this last slide, if I go from this point to the left, I see red improves, which is fine because I would like to minimize, but blue goes up. Now, locally, I have two choices. I go to the other side. Now it's the opposite. Blue goes down, but red goes up. So here in the whole neighborhood, right, and even globally, but in the neighborhood at least, there is no point which is better according to this point, according to both objectives. So this is a winner. And the fun thing is not only this point here, the graph intersects. That has nothing to do, it doesn't matter. Just for me, easier to show that you have a fixed point here. But all these points here, for all of them, the same discussion holds. So in this easy point, we see already by looking at the figure that the whole, the optimal solutions, they don't form a point, they form a set. And that's also called the Pareto set, after the inventor Wilfredo Pareto. So this is the entire set of global solutions. So this is optimal. All these line segments is optimal. This is called the Pareto set. And what we see here is called the Pareto front. The Pareto front is the image of the Pareto set, because every point here has a value f1 and a value f2. And exactly this is what we plot here. We don't plot x against f, we plot f1 against f2. So if I plot all these points there, I mean f1 against f2, I will get this Pareto front, right? So if I'm given a multi-objective optimization problem, the Pareto, well, I do not expect a single solution, but I expect an entire set of solutions, right? That is an important thing. The next thing is like a very important thing. It's not just any set, right? So if the objectives are in conflict to each other, the Pareto set even is of dimension k-1. What this is, we will see in the next slides. Bueno, aquí tenemos un problema multiobjetivo, entonces tenemos aquí dos objetivos, en generalmente tenemos tres objetivos. Estos aquí son soluciones todos, porque aquí, por ejemplo, si vamos a derecha, vamos a mejorar la curva azul, pero no el rojo. Y aquí vamos a izquierda, vamos a mejorar la curva roja, pero no el azul. Entonces, nada de estos puntos aquí en la vecindad de este punto es mejor que este punto relacionado de estos dos objetivos. Entonces, esta es una solución. Y este que dijo, aplica a todos estos puntos. Entonces, este se llama el conjunto de Pareto. Todos son optimal por definición. Es optimal por definición. Este es el problema, este es optimal. Y este es el conjunto de Pareto. Y todo este tiene F1, F2, bueno, en general hasta FK. Y si vamos a plotear este conjunto en este espacio, F1 hasta F2, hasta FK, se llama el frente de Pareto, the Pareto front. So we have this. Y el más importante ahora es no solo un conjunto. El conjunto tiene una dimensión. Esta dimensión es k-1. Entonces, si tenemos dos objetivos, esperamos algo que es dimensión 1. Este es exactamente este. Esta es una curva. Right? Es el line segment. Y este es exactamente ese. Entonces, ahora tenemos la definición de problemas con múltiples objetivos. Así es. Y ya sabemos, y vamos a esperar muchos conjuntos. Pero el problema más grande es, oiga, si voy a la tienda, y tengo tres opciones. Tú me dices, todo está optimal. Yo no voy a comprar estos tres vehículos. Yo necesito uno. ¿Sí? Solo lo que digo es, bueno, todo esto son optimal relacionado de tu problema y después es tu decisión. Pero nada de esto como es inferior. Y en el mundo real no hay tres opciones. Hay como miles de opciones aquí en DF. Y quieres un solo coche. Entonces la pregunta normal es ¿qué hago? Bueno, this we will address in a minute. I just said something is that this is the Pareto set of dimension k-1. This I will leave out. I'm a bit running late for this. you can use some mathematics to show that really that the Pareto set is of dimension k-1. El conjunto de Pareto tiene dimensión k-1, pero esto no voy a mostrar. Necesitamos unos cálculos, elementos de cálculos para eso, pero no es tan importante. Solo me creen que tienes k objetivos, el conjunto de soluciones tiene de dimensión k-1, que tienen mucho impacto. Aquí son dos ejemplos. Por ejemplo, vehículo, o todo el producto, obvio, el costo es importante y como es the performance. And the performance could be whatever you think. It could be the speed, energy consumption, emission rate, safety, comfort, whatever you want to have for your favorite car or design product. So that is all what we have, and it is very natural. And another thing is, I just put it there. I worked on this 20 years ago, space mission design. If you have a trajectory from Earth to Mercury, right? You want to make it good, and good means you want to make it low cost and you want to make it fast, right? Of course, the vehicle problem is a normal problem, and you have any idea. Space mission design is something I said, what the hell, I have never heard about this. But I put these two examples on purpose because with the vehicles, you have an idea. You have an idea what you get. If you have 10,000 pesos, you will not go to Porsche and say, hey, what do you have? Right? But space mission design is something where you have no idea. You have no idea what to expect. So if a trajectory should fly from Earth to Mercury, does it cost 10,000 pesos? Does it cost 10 million pesos? Does it cost 100 million pesos? Well, at least I have no idea. So this is the two kinds of problems which naturally arise. You have an idea, and well, you have no idea. And this also has an impact on the design of the algorithms. Okay, but first of all, as I just said, bueno, aquí hay dos ejemplos, como vehículo y como Space Mission Design, y son dos ejemplos de 1 millón de ejemplos, pero yo seleccioné esos dos ejemplos porque por el vehículo ya tienen un conocimiento, ya saben más o menos qué esperar. Si tienen 10,000 pesos, no van a Porsche y van a preguntar qué tienes para mí. Tienen una idea. Y otro es el Space Mission Design, una trayectoria de aquí hasta Mercurio, y no sabes nada. Pero estos vamos a ver también, estos problemas son normales porque tú no sabes antes qué esperar. Bueno, pero ya preguntamos, ¿por qué necesitamos todo? Porque yo quiero comprar un elemento. I want to put one trajectory which goes from here to Mercury. So why do we need all? For this, we look at this, what I call fast motorcycle problem. And for this, consider that you are very young. I think this is very easy. And that you want to have a motorcycle, but it could be any vehicle or anything else. It doesn't matter. But now you want a vehicle. And we have the objectives, cost and speed. And remember, you are young and you want to have it fast. And well, maybe your parents help you a little bit with the financing of the motorcycle. So the situation is you have a budget and you spend your budget. So the budget is for the motorcycle. You spend all the budget, and for this budget you look for the fastest motorcycle, right? So the optimization problem we have is this. It's not a multi-objective optimization problem. It's a single objective problem. So you maximize S of X, so it's the speed of X, such that the cost is less or equal than your given budget. So entonces, ¿qué tenemos aquí? Es un problema con un objetivo, algo clásico. Entonces, esta es la solución, y si resuelvo eso, esta es la respuesta de mi problema, porque yo tengo un poco de dinero y quiero gastar toda mi lana para este bici, y mi objetivo es la velocidad. Entonces, no es multi-objective, no manches, no, es solo un objetivo. Voy a resolver eso y ya. Todo hecho. Bueno, let's go further. Now we assume, for simplicity, that the speed and the cost are normalized. Well, just that I don't have to come up with funny numbers. It's between 0 and 1, right? So take your favorite numbers, but we normalize it. So for the speed, of course, 0 is 0 and 1 is 300 kilometers per hour. I don't know, whatever you want to have. Similar for the cost. And that C0, the budget is 0.5. Also, you can take any other number. And now we assume that we are given 3 motorcycles. Only 3, right? And you want to buy one. So motorcycle M1, M2, and M3. Now, these 3 motorcycles have the following characteristics. The cost of M1 is 0.5. The speed of M1 is 0.5. And now analog, the cost of M2 is 0.4. The speed of M2 is 0.49. The cost of M3 is 0.51. And the speed of M3 is 0.6. So 3 motorcycles, and you have to, or you want to choose between them. And these are the characteristics. Tengo otra vez. Tenemos el problema que queremos máxima la velocidad. La restricción es todo mi lana puedo gastar. Y tenemos 3 motos. Y estos 3 motos quieren este característico. Y estos son los valores del costo. Y estos son los valores de la velocidad. Entonces, 0.5, 0.5 y ya, estas cosas. Ahora tengo 2 preguntas para ellos. Y voy a escribir eso en el chat y vamos a ver si pueden responder en el chat, pero no, voy a dar a ustedes 2-3 minutos para pensar en eso. Y las 2 preguntas son los siguientes. Número 1 es, ¿cuál es el mejor? ¿O hay 2 mejores, 3 mejores? ¿Cuál es la solución de este problema? Ya esperamos una solución porque es el Single Objective Optimization Problem. Ok, y en el caso si hay un ganador, hay 2 perdedores, ¿verdad? Y mi segunda pregunta es, ¿puede ser que estos perdedores pueden ser interesantes? Bueno, son perdedores por definición, no, pero bueno, puede ser. Estas son mis 2 preguntas. Voy a escribir eso en el chat y ustedes pueden responder. Sí, bueno, bueno, ya ahora no ven los 2, ¿verdad? Sí, yo no sé cómo hacer eso. Bueno, vamos a poner. Sí, ahora ven otra vez. Otra vez, ahora, ese es el problema. Quiero el moto más veloz y quiero gastar toda mi lana. Estos son mis 3 motos. Ahora las 2 preguntas es, ¿cuál de estos motos, M1, M2, M2 es optimal? Es pregunta número 1. Y ya esperamos un ganador. Y pregunta número 2, y bueno, si hay un ganador, hay 2 perdedores. Y mi pregunta es, ¿puede ser que estos 2 perdedores pueden ser interesantes? Yo no digo son interesantes, son potencialmente interesantes para el que compra el moto. Ok. Ok, muy bien, ya tenemos una discusión. David dice que I go for the last option. Está bien, pero esta no fue mi pregunta. Mi pregunta fue, ¿cuál de este es optimal según de este problema? Y la otra es, bueno, una es el ganador. ¿Qué pasa con los otros? ¿Todo mal o pueden ser interesados? Ahora Blanca dice que depende del que hace toma la decisión. Bueno, este siempre tiene razón. Siempre, siempre, siempre. Siempre depende. Pero es un problema muy específica y tiene una solución. Ok, ahora tenemos. Andrés dice que M1 es lo mejor. Pero M2 puede ser interesante porque es mismo velocidad y cuesta menos. Ajá, muy bien. Muy buena respuesta. Ahora Valeria dice que she thinks that is up to the budget. No, the budget is C0. Ahora tenemos un problema específico. Ya dijo que the assumption is that we have these 3 motorcycles for the choice. We enter the shop and I said, I have this. And that's the money I have. So I have this money in my pocket and I want to spend this money. That was the assumption, right? So, and I would like to buy this. So question, no, this is I want to solve. I mean, optimization problem. The last one is out of budget. Optimal is M2. M2. Ok, muy bien. Bueno, no es tan interactivo, ¿eh? No podemos hacer, ¿quién dice M1? ¿Quién dice M2? ¿Quién dice M3? Bueno, ya veo. Vamos a hacer eso en el futuro. Pero la respuesta viene aquí. Si tenemos solo M1, M2, M3, hay solo un ganador en este caso. Porque mi lana es C0, es 0.5. Entonces, en este caso, M1 es el único, la única solución. ¿Por qué? Aquí, como alguien de ustedes dijo correcto, esta cuesta 0.51, demasiado. 0.1 es más que 0.5, no tengo este en mi bolsa, entonces no, tache, ¿verdad? Entonces, aquí este y este, bien. Este es completamente, bueno, bien, este tengo en mi bolsa, entonces la selección es esto o ese. Ahora, mi objetivo es la maximización de la velocidad. Entonces, este es mejor que ese, ¿no? La matemática dice 0.5 es más que 0.49. Así es. Entonces, we have only one winner. See, if we have more, no, we don't have, that's fine. So we only have one winner, but, I mean, and that's already, some of you mentioned this, the others are interesting in this case, because look at M2. M2, well, has basically the same speed. I mean, we lose 1%, right? I don't know what it is. If this is 300, that's 275, 95, I mean, what the hell? I mean, it's okay. Right? I mean, 295 is fine for me, but yeah, 300 is better than 295, right? But I spend 10% less, right? So I'm not saying that this is better. I'm saying this is the best according to this problem, period. There is no discussion. But this could be an alternative because this is 1% less cost with 10% less, or 1% less speed, which is essentially the same speed, but 10% less cost. Wow, right? So that's nice. This one was not feasible because the cost is 0.51. 0.51, I mean, what the hell is this? I mean, Papa pays. And I said, Papi, me das un poco más. Huh? So if Papa pays some pesos more, or you find them somewhere, right, you have a bike which costs a bit more and too much for this problem, but gives you 10% more performance. Right? So I'm not going to tell you which is the best. I can tell this is the best according to this problem. But I never said this is the best problem. I already told you, if you ask the wrong question, you get the wrong answer. Right? Because I say in this particular case, all these 3 are candidates. And then some of you said completely correctly, it's up to you. Well, it's up to you. I mean, you want to save 10%? And buy a motorcycle helmet, that's fine for you. You want to ask Papi, say, Papi, give me a bit more money. I want to have this kick-ass motorcycle. No, that's okay, right? So that's fine. Just that's what I want to say is that you have to check the alternatives. Okay, good. So again, I mean, now in very general terms, if we have the, En español, sí, motor 1 es la única solución de este problema, pero estas son alternativas. Este cuesta 10% menos, pero 1% menos de velocidad, entonces más o menos lo mismo. Y C3 es demasiado caro, pero solo 1% más caro y me da 10% más de velocidad. Entonces, son 3 alternativas interesantes. Y en general, no hablamos de motos, de nada, hablamos de F1 hasta F2. Si tenemos todas las soluciones, solo para presentar, no para comprar, no compro todos los coches, pero si tenemos todas las soluciones, bueno, ahora podemos ver, ¿sí? ¿Qué pasa si compro A o B? Y la comparación de A a B es fácil. So if I change from A to B, so I think about bike A, but your wife said, go for bike B, and then or product B, whatever that is, and then you see exactly. You said, if you go from A to B, you win this part or you gain this part according to F2, but on the same time you lose this part according to F1, right? So you change from A to B. So delta 2 is your gain, and the sacrifice is delta 1 according to F1. So this is what you see. I will not say take A, take B. I mean, this depends on the problem, but you present it to the decision maker, right? And that's it. So if you go and buy a Marshall, well, you go and buy the Marshall. But if you produce the Marshall, then you say, hey, in which market segment do we want to be? I mean, if I increase a little bit, I can make 10% more power. And then the people are really interested in the new Marshall, right? So that's something which might be interesting. Okay, another thing which might be also interesting is the so-called knee solution. Sometimes, not always, but sometimes the Pareto front is a bit like this, right? So a bit extreme. And this knee point, when we have this point, all the people like this point. Why do they like this point? Because, it's not the best, because that's what Pareto says. All of them are optimal. But look at this. You take this point and then you move to this point. Okay. You make a gain of F2, which is marginal, but you have a huge sacrifice. And here's the opposite, right? So the knee solution might be interesting for you. So whenever we had a trouble and a problem, a real-world problem, well, an application, and we had this shape of the Pareto front, I'm sure that the designer said, hey, that's a good point, right? It's okay. You don't know in advance. But nevertheless, I mean, even if you have this point, people like to compare. I said, okay, your cost is 10,000, but what else can I do? They would like at least to see the solution, right? So seeing the solution makes you fine, because that's the same thing. You go to Sears, you go to Liverpool, if it's all the same price, and you are in Liverpool, you take the box, right? It's the same thing. I mean, you would like to see the options. So here, the thing is, of course, we are not buying a manifold of solutions, but if we have the solution for you visually, then you can make this the basis for your decision-making process. You can so choose this point or here, whatever you want. Bueno, aqui em 2 dimensões vemos que podemos ver se temos al frente de conjunto que podemos ganar y que es el sacrificio, si tenemos 2 puntos. Y aquí es un punto extremo, se llama la rodilla del frente de Pareto, porque si este es una pierna, este es la rodilla. Bueno, así es el nombre. Y aquí vemos que es preferible para mucha gente, porque si vamos a hacer la comparación de otro punto, bueno, hay un gran sacrificio en esta dirección por solo un poco de ganancia. Okay. Depende completamente de estos valores, de su preferencia, pero bueno, así es. Estos son los puntos. Entonces, lo más que sabemos, lo mejor. Bueno, now we have an example. Before I come to another thing, it's something we did 20 years ago together with some engineers in Paderborn, and they had the cooperation partner was Mercedes, and they had these active suspension systems. So it was here a suspension system. Active means that you could, while driving, change the performance, right? I mean the adjustments. And the 2 objectives were the comfort. In Germany, they even have a DIN norm, an industrial norm for the comfort. And comfy means that you drive around and you feel fine, you don't feel the bumps, right? So the damper takes everything out. But also you would like to have a safe car, of course, and that is the displacement. Displacement means you would like to follow the car. Aquí es un problema que hizo como antes de 20 años, antes muchos años, Active Body Control. Aquí es una suspensión de un coche y los objetivos son el confort de como ser en este coche y como seguir la calle, displacement en español. Y bueno, yo no voy a hablar de estos detalles, entonces ya hicimos el frente de la computación para el frente de Pareto y todo fue fácil. Todos los frentes de Pareto ven como más o menos así, pero ahora es interesante, ahora Pareto comes alive, right? Entonces todos estos puntos significan otro suspensión. Y ahora tenemos un vídeo, un poco extremo el vídeo, y tenemos tres coches, y estos coches tienen tres suspensiones. El azul, coche azul quiere seguir la calle completamente. El rojo, como el confortable y como el oro es como el compromiso de oro. Entonces vamos a ver ahora este vídeo varias veces. Que vamos a ver aquí es como una parte de una calle. Primero vienen topes completamente extremo como DF y después una rampa. Y vamos a ver qué pasa. Y primero vamos a ver este coche que es confortable. Quiero como confortable, I damp everything out. Ok, vamos a empezar. Ah, no, eso es en... Yeah. Ah, ya, perdón. No ven bien, ¿verdad? Es siempre así, la primera vez así. Ok, ahora es en los topes y como completamente confortable, ahora viene la rampa y obvio no puedes poner ese. You cannot damp out this disturbance, so it doesn't work, right? It's very nice in a bad road, but at the end it's not good because you cannot completely follow the street. Though it is optimal, but the emphasis on comfort. Now we look at the same video, but we look at the blue car, and the blue car would like to follow all the road. And we see at the bumpers, I mean, nobody wants to sit in this car. I mean, it's terrible, right? But the ramp enters very nice. So we follow the road. So that's nice. It's still optimal, but nobody wants to sit in this car if it comes to rough times. Here, now we look at the car in the middle. It doesn't have to be in the middle, but here it is in the middle. It's the golden compromise. We see we can handle both. Here we are not as good as the red car, which is okay, but we can handle both. We can go up the ramp. We can go there. We are better in the bumpers as this car, and going up the hill, we are much better than this car. Bueno, ahora la última vez tenemos tres coches y este coche que es confortable, este coche que quiere seguir todo, este es el coche como el compromiso y este coche aquí está muy bien en los topes, pero no puede seguir la rampa. Este aquí es el opuesto, es como el infierno en los topes, pero después sí puedo seguir la rampa, entonces algo que está bien, es más seguro. Este coche en la mitad, como es entre estos dos extremos, es mucho mejor. Entonces, ahora no digo, este es el mejor coche, yo digo, ustedes tienen ahora como una sesión interactiva y ustedes pueden hacer la decisión. Si quieren un coche que es como más deportivo, bueno, está acá. Si quieren un Crown Victoria, obvio aquí o más, ¿verdad? Entonces, estas son las tres opciones y ya, este es un ejemplo donde pueden ver si está bien tener todo, porque no sabes antes qué es la solución. Es lo mismo como el Fast Motorcycle Problem. Antes no sabes nada si esta solución es exactamente qué crees. Y también si preguntaste esta pregunta, pero como he dicho varias veces, la pregunta no puede ser ideal. Yeah, well, this is one thing, and here is even well, I will skip this. That is not so important. We made online optimization with this, but it doesn't matter. Okay, now we already agreed if you have all the Pareto set, everything is fine, right? Because you have all the data, you have the basis for the optimal decision making, everything is fine. No. Everything is fine in two objectives. So I have here 100 points, 200 points, 500 points, I don't know. And then I can make the decision. I said, well, what do I get here? What do I get here? Well, that's two objectives. Now, we have three objectives. We have F1 against F2 against F3. So the Pareto front is a two-dimensional set living in three-dimensional space. Well, still everything is fine because we can make a selection. Like These points here are here and here or wherever. And then, of course, it's a bit bad because it depends on how I do it. Three-dimensional plot is always a bit nasty, but yeah, I can do it. But that's it. Now, for objectives, I cannot plot in four objectives. So in four objectives, I can still plot projections. F1 against F2 against F3. F4 is out. F1 against F2 against F4. F3 is out, and so on. So these are four projections. Now, every point here has 1 point here, 1 point here, 1 point here, 1 point here, and every point here, yeah, has another 4. And then we have 4 times the same trouble I already mentioned you. And that's 4 and 5. Yeah, come on, right? So there is no way. And on the other side, there is also no way to reduce every design to 3 objectives, or maybe 4, right? Because a car, you cannot break down a car in 4 objectives, right? There is more. You want more. This is your dream object. So there are 10 objectives or more, right? So that's the point, right? And here we have 2 problems, and we call it the curse of dimensionality. Bueno, ahora esa es la decisión. Podemos hacer en 2 objetivos, puede ser en 3 también, pero en 4 o más no es posible, porque no podemos plotear en muchos objetivos. Este no es posible. Ese es, no sé, the curse, I don't know this en español, de la dimensionalidad. Entonces, tenemos problemas, son 2 problemas. The first one is how to discretize the set. I mean, here, maybe I need 20 points, 50 points, 100 points. But if I need 100 points here, I need 100 square points here for the same quality. And of course, here, 100 to the power of k minus 1 to the same point. So that grows exponentially. So even, for instance, if we only take 3 points here, the 2 extreme points and the middle point is not a good approximation of a line, right? But if we take these 3 points, we need here 9, here we need here 27 points. And if we have, for instance, 14 objections, we already need 1.6 million solutions to get something which is not sufficient, right? So we cannot compute it all. But even if we compute it all, right, I compute 10 billion solutions. It's fine. Then please go to your boss and tell him, here, your 10 billion solutions, what do you want? They sent you to hell, right? I mean, that's not the way, right? So that doesn't work. Ahora vemos que uno de los problemas del Curse of Dimensionality es que si tenemos más objetivos, tenemos mucho más puntos para la aproximación para tener todo el frente de Pareto. Entonces, ¿qué vamos a hacer? Y el otro problema es la decisión. Si tenemos 1 millón de puntos, ¿qué hacer con eso? No puedes decir a tu jefe, si tienes 10 millones de puntos, ¿qué prefieres? No van a evaluar. So what we do in the mathematical programming literature is we divide the problem. We say if we have 3, maybe 4 objectives, we call it a multi-objective problem. And if we have more than 3 objectives, we call it a many-objective optimization problem, right? And it is mathematically absolutely the same, but the curse of dimensionality forces us to use different methods, because here I can compute all, maybe here, but if we have 14 objectives, computing all is no way. And even if I can do it, we cannot evaluate all the points, right? So that's why, from the practical point of view, we have multi and many objective optimization problem. That's why it's the same introduction, but there will be different methods for this. Entonces aquí, por eso Curse of Dimensionality, vamos a separar los problemas en problemas con múltiples objetivos, si tenemos 2, 3 o 4 o 5 objetivos, o otro es el problema con muchos objetivos, porque necesitamos otros algoritmos para tratar estos problemas. Muy bien. Okay, so here I stop with the definition of multi-objective optimization and many-objective optimization. I mean, you have seen multi and many-objective optimization is everywhere. The world is getting more and more complex. That is, the decision-making process is getting more complex. So there is a recent trend to look at more at only 2 objectives. So many-objective is the current future. Question is, of course, how to treat them. I mean, these I make very, very short. I just present some basics, but well, let's do it now. The methods you can divide roughly in 2. I do it into 3 categories. There is mathematical programming. in mathematical programming is what you do is you take a point and you iterate this point. They're called point-wise iterative methods. So you have a point, you make your magic, you get another point. And this sequence of points hopefully converges to a good point, right? So this is what you get. There are scalarization methods, there are descent methods, there are interactive methods, but they all have this. You get 1 point and then another, and at the end you get 1 point, right? So you reduce the problem to a single objective optimization problems. I talk about this later. Then there are set-based methods. So methods that say, well, I'm expecting a set, so I'm going to take a set and then to evolve this set to see what happens. So this set should ideally approximate the entire set. Most popular are evolutionary strategies, but there are also subdivision techniques and cell mapping techniques. And finally, there are continuation methods. Continuation methods perform a movement along the Pareto set because they take advantage of the fact that the Pareto front is a manifold. And if it's a manifold, you know that in the neighborhood of a good solution, there is another good solution. So why not tracing this set of good solutions, which works locally the best you can do? That's my opinion. Bueno, ahora tenemos 3 clases de optimización. Son Mathematical Programming, son problemas punto a punto que generan un solo punto, la mayoría de estos métodos. Hay como conjuntos o algoritmos basados en conjuntos como métodos evolutivas, que son muy bien, que trabajan en un conjunto de elementos. Y tenemos métodos de continuación, que yo creo que es lo mejor que puedes hacer localmente. Yo hoy no voy a hablar de set-based methods, voy a hablar de los otros métodos un poco. Set-based methods hay en unas semanas, creo que julio 28, la plática de Dr. Cuello que va a hablar de estos métodos. Y también voy a hacer un poco publicidad para mis libros, pueden ver mis libros, leer mis libros para ver un poco más de estos set-based methods. Un libro es de cell mapping methods que incluye también los métodos de subdivisión y los otros es para qué hacer que los métodos de evolutivas convergen con probabilidad 1 hasta a la aproximación al frente de Pareto. Bueno, I will talk a bit about mathematical programming techniques first, and by far the biggest class is Calorization Method. So I take the problem and transform it into a single objective problem. We already had one. That was the fast motorcycle problem. We already seen the advantages and disadvantages. Advantages, you get something, and you can put your knowledge inside. So that means that you expect that this something makes sense. Right, but we have seen not always, right? But all of them work like this. So you have some external parameters, and you use them to steer the search toward the right solution. And that was the epsilon constraint method. Another one is the weighted point method. That is a very widely used technique, and it's as follows. Métodos de escalarización, transforman el MOP, el problema con múltiples objetivos, a un problema con un objetivo. Esta es la idea. Y a un ejemplo que ya sabemos es el Fast Motorcycle Problem. Este fue nada más que una aplicación del Epsilon Constraint Method. Y otra es punto de referencia. And well, that's very widely used. You're working in a company, and your boss asked you to design a car with this cost and this speed. But your boss is your boss, right? And he tells you something which is on favor of him and the company. And it might be that it's very likely that this car with this speed is nothing you can do. So, and then you have two things. I mean, you can say, hey, boss, I cannot do it. It's correct, right? But it doesn't save your job, right? The other thing is you can go to the boss and say, boss, you know, with 10,000, I cannot do it. But if you give me 11,000, I think we can do it, right? And mathematically, this is the reference point method, right? So you have a reference point. So you have the ideal point. This is the point your boss gives you. That is the performance you would like to have, but you don't get it, right? So either you do nothing or you do the best. And the best is you find the point which is closest to this point. Here is an example, F1 against F2. Here is the Pareto front, well, and here is the utopian reference point, right? And this point, this point here is the closest to set, right? Here, this one not, this one not, this is the closest to set. So and that is the solution you compute. This is the solution you go to the boss. I said, well, this cost, this speed, not, but for 11,000, I get this speed, right? And then you can discuss. Entonces, this is the reference point method. El método que utilizan muchas personas es como el punto de referencia. Si tienes un punto de referencia, bueno, haces lo mejor que puedes hacer y haces la optimización es ese. Minimización de X, de D, Fx y Z. Z es el punto de referencia. Fx, bueno, es el performance que tienes por todo X. Y D es una distancia. ¿Cuál distancia que quieres? ¿Verdad? So this is the reference point method, and that works fine. It has the same advantages and disadvantages as the epsilon constraint method, because you get something which might make sense, but well, doesn't have to be exactly what you need, because the solution of this point, well, of this problem, this is the problem, and this is the picture for the problem. The solution of this problem depends on three things. It depends on the reference point. Apparently, if you put the reference points here, well, you get another solution, right? If you choose another distance, not the 2 norm, but the 4 norm or whatever, then you get another point. And that's something to say, well, it is in my hands. I know what to do. But it also depends on the shape of the Pareto front. But you don't know the shape of the Pareto front, because that means you compute all. What we just said, we don't want. We just want 1 point, and that makes no sense, right? So what I want to say is that this is maybe the solution of this point is maybe a good starting point, but it is not exactly what you want, and it is not in your hands, right, to compute these things. So that's the thing. So all of them have advantages and disadvantages, right? So that's here, but it's the same for the experts. The expert will tell, hey, Dr. Oliver has given the easiest of the reference point methods. There are 30 out in literature, and maybe the achievement scalarizing function is the fanciest one of them. That's true. The achievement scalarizing function is the fanciest of them, but it would take me 30 minutes or 20 minutes to explain you the method in detail, but it comes with the same advantages and the same disadvantages. So that's my point. All of them have the same. All of them are fast motorcycle problem, right? With their own advantages and the disadvantages. Okay, muy bien. So now this is the reference point method, and I have 1 point. The 1 point, of course, here we have to distinguish the 1 point. I mean, if you buy a car, you know what you want to get, right? But if you fly to the moon or to the Mercury, you don't know anything, and that's of course a very important thing. So this is not good. But set plays a funny role. So what happens if I don't take 1 set, but I take 6 values of set, right? So I take these 6 values of set. So that means that I have to solve 6 of these problems. So if I solve 6 of these problems, then I get this. And I only took 6 because, well, my picture here, I mean, I cannot plot more. If I plot 20, we will see that we will get a Pareto front approximation, and the Pareto front approximation looks good. So if I put 20 good points, I will get a good Pareto front approximation, and that's exactly what people do. So they use set to steer, or the external parameter of the scalarization method, to steer to get a Pareto front approximation, right? So that's another thing. But of course, here the trouble is how to choose set. I mean, if you know the shape of the Pareto front, it's pointless, because then what the hell, right? So there are methods who do that, and the method I just mentioned before doesn't change that. Actually, it changes the distance function, but it's the same thing. I mean, you use these scalarization functions and you use their external parameters in order to get a clever sequence of single objective problems. And this clever sequence of single objective problems delivers you a nice approximation of the Pareto front. But it only works if the sequence is very cleverly chosen, and that's the problem. So no problem, no of these approaches comes for free. So getting these clever sequence Sometimes it works, and still in some cases it doesn't work. So this is still a drawback. Entonces, en español, puedes utilizar estos parámetros externos para generar puntos en el frente y para tener una aproximación de estos puntos. Pero el problema es cómo poner estos puntos, estos parámetros externos en una manera bien. No sabes que es bien y depende del problema, pero bueno, en muchas ocasiones sirve bien. Entonces, estos fueron, bueno, los métodos del mathematical programming. The other thing is a continuation method. I told you I leave out all the set-oriented methods. Here, don't look at this, look at this, right? So we know here is the Pareto set or the Pareto front, and we assume we have an initial point. Okay, we have this initial point. What we do now is we linearize the Pareto set. How? I will tell you in a minute. Well, not really, but I will talk about this, right? So we linearize the set, we go in this direction, and then we project back. How? I will also tell you later, but we project back. So then we have x0 and x1, 2 points on the front. Then I linearize my set again. I assume that this is linear, I linearize, and then I project back. So like this, I get a sequence of points which moves along this Pareto set, right? And of course, if I choose this step size accordingly, I get a good approximation of the set. Now, mathematically, what do we do? Again, I will not tell you the details, but it's what we need is a root finding problem, right? And if we have this root finding problem, and this will be the first order Karush-Kontaka conditions in our case, I can apply the implicit function theorem, which is a powerful tool of algebra, calculus, and I know that this exists theoretically, but it's an existence theorem. We don't really need this. This is of no practical use. In this case, yes, because if I use this trick, I use a differentiation, and I see that I have a kernel vector here, I can transform this problem into an ordinary differential equation. That's the linearization, actually. And then I can proceed. So then I linearize my problem. That is the linearization here, right? And then I go in this direction for a stretch, knowing that my curve is a curve and not linear. So I have to project back, and then I make use of the fact that I have a zero finding problem. Otra vez, we have a given problem. We compute our initial value problem, so we have a vector field. We follow this vector field for a certain stretch, go in this direction, it's linear, of course, project back, linearize, project back. So that's what we do, all right? So, and I would say that, or I say that this is locally the best you can do for multi-objective optimization problems, but it is local. I mean, all these things are on a connected component. If the Pareto set consists of several connected components, which can happen, the method will not be able to do it. So they can only do it locally. If the front ends here and continues here, this method will not do it because they shoot in this direction. So there is no way to get something. But locally, so on this set, my claim is that this is the best you can do, right? Okay. Good. Entonces ahora tenemos métodos de continuación. Esto no voy a explicar, perdón, pero que vamos a hacer son métodos predictor-corrector. Vamos a generar puntos en dos pasos. El primer paso es una linearización del conjunto y después vamos a hacer una proyección. Entonces, linearización, proyección, tenemos otro punto, linearización, proyección. Este es con los elementos muy básicos, faltan muchos detalles, pero estos detalles no puedo explicar hoy. Por ejemplo, necesitamos una orientación de la curva porque no podemos ir en esta dirección y después vamos atrás. Pero este existe y la idea elemental es exactamente esa aquí. Yeah, and one of these continuation methods is the Pareto Tracer, right? It falls absolutely in this category. The distinction is that here we would like to separate the weight space and the X space, which is something you cannot understand because for this you have to look at the Karush-Kontaka conditions, which I have not showed you, so it doesn't matter. Bueno, uno de los métodos es el Pareto Tracer de 2018, bueno, publicado en 2018. Este es en la misma manera que el otro que expliqué, con variaciones, obvio, pero para ahora no está tan importante. Y puedo resolver problemas muy eficientes. Por ejemplo, aquí tenemos un problema con 500 dimensiones y con una restricción igualdad, y podemos resolver este problema con menos de 1000 evaluaciones de función. Este es algo que es maravilloso. Ese no puedes hacer nunca, nunca, nunca con métodos evolutivos. No es posible. Pero métodos evolutivos son una manera global y este es local, entonces no puedes comparar aquí. Yo digo, localmente lo mejor que puedes hacer es ese. Ya, bueno, es así. Ese es un método y voy a hablar de esto un poco más tarde. Ya podemos hacer 3 objetivos sin problemas, pero también tenemos el Curse of Dimensionality. También cualquier método que tienes, si tienes 18 objetivos, bueno, el conjunto de soluciones tiene dimensión 17 y no puedes hacer eso. Entonces, este está bien para multi-objective problems, pero no para many-objective problems. Y para many-objective problems, bueno, hay muchas cosas, muchos algoritmos. Yo voy a hablar solo de uno de estos que hicimos en el SimStaff, en mi grupo, y es el Pareto Explorer. Y la idea es que empiezas primero con un punto, puede ser la solución de este reference point method o de cualquier método evolutivo que sea. Ahora necesito su imaginación porque este no es un conjunto de dimensión 1. Piensan aquí en dimensión 15. Yo no puedo dibujar ese. Bueno, entonces empiezas con ese punto y este es el punto inicial y después el decision maker dice, me gusta ir en esa dirección y vamos a hacer exactamente eso. Right? So this is what we do, and what we do in fact is the Pareto Explorer in its current implementation is based on the steering properties of the Pareto Tracer. The Pareto Tracer has a lot of steering properties which I didn't mention. I just mentioned here on this picture how we can make the steering in objective space, right? So assume we have given this point, and here's the Pareto front, and the decision maker said, you know, this point I don't like. I would like to go in this direction defined in objective space. Okay, why not? Well, no, because this direction is not feasible, because here are no points which we can compute. We cannot do this, but what we can do is we can compute the best fit direction. We compute the tangent space, we project this point to the tangent space, and then we move along. So that means in this case, we would move down, right along the Pareto front. But again, here I ask for imagination. This is not one-dimensional, this is 15-dimensional. So here there is not left up and right down in 15 dimensions. There could be whatever. Well, you have a basis of dimension 15, right? Of course. So that makes sense, but we can still do the same. We can do a best fit approximation, right? And this is exactly where the algorithm is designed for. We have 15 objectives. You have any idea where to go, the decision maker, we do this, right? Entonces, esta es una manera para hacer el steering, para manejar, y este es el steering objective space, pero tenemos 6, 7, 8 cosas diferentes. Algo completamente parecido es la steering en decision variable space. Tenemos en los the weight, podemos ir al lado de la rodilla, podemos explorar toda la vecindad en una manera buena. Y otra cosa es un poco chistoso, pero tengo un vídeo para ustedes en un minuto. Podemos reducir el movimiento en el espacio de objetivos, porque, bueno, la gente están aquí por razón, porque este es un coche costoso o esto es un reloj barato y quieren así, porque la gente no quiere comprar un Zuru caro. Zuru es barato, punto. Y quieren ser o estar en este segmento del mercado. Entonces, ese tenemos también. What you have to think is that the Pareto Tracer is a device to locally explore the Pareto landscape. So here, of course, this here is the Pareto landscape. 15-dimensional is rough, and here is our car, right? That's the Explorer, right? The trouble is that is not the right picture because you don't see the Pareto landscape. So I should see that this you should do in the night. But I mean, that doesn't make a good picture. It makes a black picture, right? So it's like Pareto front by night. So that's what you have to have in mind. So we can steer it in various cases. So we have a point, and then the decision maker says, no, I would like to do this and this and this. And that is exactly what we can do. And we do it, and that's in between of the two extremes. All you cannot do, and one point, that's here the solution of the first point. We just had it, fast motorcycle problem, might not be what you want. Right? It could be, but it could be not. Right? Y ahora tengo tres ejemplos. Un ejemplo es con una colaboración con Canegisa. Canegisa es una empresa alemana y ellos hacen como, bueno, máquinas lavadoras. So they have washing machines, and these washing machines have to be good, of course. And they have to be good, and sorry, I don't know all the details, but they have to be good according to wool grease type A, or whatever that is. They have to be good according to wool grease type B. Red wine, the motor oil, extra, cocoa, right? So 13 different objectives. Maybe they're related, I have no idea, right? So I think starch and cocoa, are they related? Ask a chemist, not me, right? So I have no idea. So for me, they are 13 different objectives. So they want to make it good, and this I understand, they want to make it cheap, right? So it has to be of low cost. Here are some parameters, there are just a few. The thing is that we cannot give all the details because it's from a company, they don't want to give out details, but nevertheless, 14 different objectives, and this is a real problem. So we cannot compute all, well, in real life, in here shortly, yeah, but we cannot compute all, so we use the Pareto Explorer. So here I will give you two animations. The first animation, well, there are two different scenarios. Well, we don't know, cannot compute the Pareto front. So what we do is here, right? I mean, we start with a high quality solution, which has a high cost. So it's good, but expensive. So I say, what happens if we reduce the cost? So F14 is to be minimized. So the steering and objective space is minus E14. So you just see what happens if we decrease the thing. So now I will show you here an animation, but for this animation I have to tell you about the Pareto Wheel, because we have to see what happens with 14 different qualities or objectives. So you cannot plot them in 14-dimensional space, but what you can do is you can put them here on the circle, on the standard circle, and you can divide the circle here into 14 different objectives. And now the thing is that if a point here is closer to the circle, to the boundary, it's good. And if we go inside, it's bad, as is. So now that is something we call it Pareto Wheel, right? So we can compute or display different qualities, 100, 200, whatever you want, right? Here we have 14 and 4. Now let's show the video. Bueno, perdón, aquí es la rueda de Pareto. Aquí, esta es una manera para mostrar los objetivos. Aquí tenemos 14 objetivos. Vamos a poner los 14 valores en un círculo. Y lo más cerca del punto es al frente de este círculo es mejor y adentro es mal. Por ejemplo, aquí estoy muy bien de calidad 1, muy bien de calidad 2 y 3, pero muy mal en el costo. Bueno, el costo está muy alto, este es mal. Exactamente, este es donde vamos a empezar. Ahora, la animación. Aquí vemos el X, ahora los objetivos, los 14 objetivos. Voy a mostrar otra vez, pero aquí vemos estos cosas en una animación y cómo se cambian por tiempo. Y que vemos aquí es el espacio de objetivo, aquí es F14 y F14 fue el costo. Y que vemos por el tiempo, aquí va aquí más y más y más al frente, entonces va a ser mejor y mejor y mejor. We see here it's getting better over the time. So I get a solution which is less costly. Ahora en el mismo momento, aquí F2 va a ser peor. F3 casi sin efecto. F5 peor. F9, F10, F12 menor. Y F11 no mucho efecto. Así es. Entonces, ¿qué vemos aquí? Bueno, nada. Vemos la evolución del tiempo, pero no puedo decir. Puedo decir, ajá, aquí el costo está mejor. Pero aquí, por ejemplo, F2 va a ser significante peor. Y esto es algo que depende completamente del señor, la señora que hace la decisión. Entonces, este está bien, es aceptable, está bien. Terminas aquí, está bien. Entonces, este es como el sistema de experto, el expert system que llamas. Entonces, tú tienes tu Jeep, tú tienes tu Pareto Landscape y vamos a ver qué pasa. Entonces, vemos que sirve, pero no vemos mucho más, porque esto puede ser que sí o puede ser que no. Ahora, por eso tengo aquí otro ejemplo que está como más como claro. Ahora tenemos otra vez otra solución que es como high quality and el tiempo para lavar está grande. Entonces ahora vamos a hacer lo mismo, pero el steering, el cambio va a ser UX o DX es menos X3. Entonces quiero reducir el tiempo para lavar y vamos a ver qué pasa. Aquí en X, aquí en Y. X3 tiene que minimizar. Esto es exactamente lo que vamos a hacer, ¿no? X3 está menos. Vamos a ver otra vez. Aquí veo que tengo que ver. Aquí veo, bueno, yo no sé qué ven ustedes, pero yo veo casi nada. Entonces, cambia un poco aquí en F11, F12, pero no cambia mucho. En estas son buenas noticias. Ahora, este video aburrido es el mejor video que tengo, perdón, no tengo más, pero este es algo que puedo explicar a todos. O sea, el tiempo para elevar es la mitad, pero la calidad, básicamente, aquí hay diferencias, es lo mismo. Si puedo lavar el curry por 88.8%, 88.7%, bueno, este no hace para mí mucha diferencia, pero ese yo veo. Entonces, en ese ejemplo, y este fue el punto donde Carnegie fue feliz, en ese punto ya sabíamos que el Pareto Tracer ya tiene sentido, porque aquí tenemos un ejemplo donde el washing time, el tiempo para lavar, es la mitad, pero por la misma calidad. No, obvio, si el tiempo es la mitad, puedes hacer en el día lo doble. Entonces, este es dinero, ¿no? Este fue muy bien. Ok, este es mi gran ejemplo para problemas con muchos objetivos. We have another one, but in principle it's all the same. The videos look all the same and they're not as beautiful or boring as the other video, but in principle they're all the same. Another thing we have is plastic injection molding, right? You know, little plastic elements like these ones here. This is a plastic gear. They are molded by these plastic injections. So you inject it into a form and then you get this. This is the fastest and cheapest way to get it. And of course, still you want to make it good, you want to make it cheap, and you want to make it fast. And these are the 7 objectives we have identified. Well, this was in collaboration. I didn't identify anything. I used the Pareto Explorer. But here we have an example, which is also like real life. And we see we cannot reduce it by 2 objectives. It's 7 objectives. We cannot compute it all. And here, well, we have several papers published where we showed that the Pareto Explorer had a certain advantage. Aquí es otro ejemplo. Es plastic injection molding, esta es una manera de hacer piezas de plástico y como todas las cosas quieres hacer bien, barato y rápido. Y este exactamente fue el estudio. Aquí teníamos 7 objetivos y con estos 7 objetivos, bueno, no puedes tienes todo el frente de Pareto, pero utilizábamos el Pareto Explorer y este fue un éxito. Bueno, ahora estoy listo. I'm ready with my talk. Thank you very much. I'm just having another 2 slides. This is the summary. So I introduced very roughly to multi and many objective optimization. So I give the definition, you know what the Pareto set, what the Pareto front is. You know that this is of a certain dimension. You know that this comes with a curse of dimensionality, so that you know why why multi and many objective optimization, well, it makes sense to have different terms for them. You see the challenges. Of course, we only want one solution, but we want to compare. I mean, that's something very general. I mean, we would like to compare before we buy something. At least I wanted, and all the people I came across with, they want to be sure that they get the right solution, right? And if you buy something, okay, you just go to the store. But if you design something, I mean, then multi and many objective optimization is a strong tool, which comes with the challenges, which is given by the Curse of Dimensionality. But you have seen is that it arises everywhere. So I came up with well, hundreds of little examples, and they lead to real world examples. And these real world examples, it's not solved in 5 years, so it will be still active in 10 and 20 years. I think multi and many objective optimization will be good. Other things approach, but optimization in very general terms will be relevant in 10, 20, 50 years. I'm sure about this. And I did talked about methods, but that was a very slow part, a very weak part. But to give you the real methods, you need to go to see the optimization classes which I give, and that exactly leads me to the point. The thing is, if you're really interested in this, you want to work on this, theoretical or non-theoretical, well, you have to decide for a career in optimization, and that's what we have to offer, right? The SIM stuff. Well, in general, in Mexico there are many places. One of these places is the SIM staff, the computer science department, where we are dealing with such optimization problems. Entonces quiso hoy una introducción muy básicamente a los problemas con muchos y múltiples objetivos, la definición, el conjunto de Pareto, y este dice que tenemos una Curse of Dimensionality, la dimensión de este conjunto puede ser muy arriba. Entonces tenemos esta distinción. Matemáticamente es lo mismo, pero hablamos de problemas de múltiples y muchos objetivos, y para eso necesitamos otros, ¿cómo se dice? Otros algoritmos, y para todos hay muchas aplicaciones. Y yo creo que esa optimización y multi-objective va a ser relevante por los próximos 50 años. Hoy solo hizo poner unas palabras para la introducción, pero si se interesa ese, bueno, una opción es ir al SimStaff, donde tenemos muchas personas que hablan en la área de optimización, no solo yo, son varios que hablan en esta área. Y bueno, puede ser una opción. En un minuto ya estoy abierto para preguntas, pero antes de eso, bueno, antes de terminar, voy a hacer un poco de publicación. Yo también tengo cada año, nosotros tenemos cada año un taller. Este taller se llama Numerical and Evolutionary Optimization, que llama, bueno, de optimización. Va a ser en el septiembre 9 y 10. Pero en el septiembre 8 tenemos el Research Experience Day. El Research Experience Day es más o menos como el SimDescom, y bueno, enfocado no en Computer Science, pero en optimización. Entonces, si está interesado para ustedes, están más que bienvenidos a ir al Research Experience Day. Ok, es todo de mi parte. Muchas gracias por su atención. Y bueno, estoy abierto para preguntas ahora.
Hola, buenas tardes.
Hello.
Cuando hablamos de optimización, pues obviamente se entiende que es una parte teórica que a lo mejor no se puede obtener el resultado óptimo el 100% de las veces. ¿Qué nos puede decir usted referente a eso, de esa diferencia que existe entre la vida real y la teoría, de cómo la vida real no se puede asemejar a encontrar el resultado 100% óptimo?
Yeah, very nice. There are a lot of flavors of the answer. I hope that I get the right one. Now, there are a lot of answers. One is uncertainty, for instance, and the other one is, yeah, the most classical answer is that a method, well, is mathematically convergent. So you get x1, x2, x3, all these candidate solutions which converge to the optimal solution. But convergence is a mathematical thing. And a mathematical thing says, I have it in the limit. And that's not 10,000 elements. That's whatever. I mean, that's not even 1 million. I mean, it's to infinity, right? So and you have to stop and you have to say, well, that's fine, right? But that's also okay. I mean, if you build a bridge and the bridge has to have a length of pi, and nobody can build a length of pi, right? So it's 3.14 meters, that's fine, right? So in many applications, you know, or you have to, well, sure, you have to ask before for the how to say, for these thresholds. For the thresholds, is that what can we do? So is it accurate to 1 centimeter, accurate to 1 millimeter? So that's very important. But if you have these values, then you can be fine. So that's, I know a lot of applications where you solve them and everybody's happy.
Yeah.
But there are also others where people are not happy and it's their uncertainty inside. So I said, like portfolio, I said, what should I buy? I mean, in what assets should I spend my money? And I mean, by definition, you don't know this before because you minimize not the risk, you minimize the expected risk and you minimize the expected win. And that's something which is already in the definition. I mean, you don't know it in advance. That's another story. Today, I didn't talk about these things, but yeah, that's a very important stream.
Thank you very much.
Okay, yeah, there is a question for the Pareto Tracer and the Pareto Explorer, the tools. Yes, the Pareto Tracer is online. We have the code. This is in GitHub, so that is fine. The Pareto Explorer yet is not available. I mean, we have a version which is for research. We can use it. We also give it away, but it's not already like completely done in the sense that we have already documented it. But on request, we can give it out. Yeah, please send me an email if you want to have it and how you want to have it, and then we can discuss. The other one, the tracer, is fine, and this is publicly available, so you can download it, and it's well documented with examples. And the other one, not yet. We are on it. Bueno, sí, ¿hay otras preguntas? Ah, sí, hay una aquí. For the Pareto Tracer, how do you get the initial solution? I mean, el punto inicial, buen punto. No, necesitas el punto inicial. Para el Pareto Tracer, normalmente, ¿qué hacemos? Tenemos cualquier punto, y cualquier punto empezamos con el método de Newton. Y el método de Newton hace la proyección hasta el frente de Pareto y después haces el resto. Pero como digo antes, el Pareto Tracer es un método completamente local. Local es lo mejor que puedes hacer, pero es local. Y local dice que puede ser con un punto inicial, vas a ir al infierno, a un punto que no está tan bueno. Entonces, otro trabajo que no mencioné es hibridizar el Pareto Tracer o todos estos métodos locales con métodos evolutivos. Hacemos mucho. Y este es el producto final porque es como fast and reliable. Entonces, tienes puntos que son un algoritmo que está rápido y completamente, bueno, la solución está bien. Tenemos recientemente papeles en esta dirección. Okay. Ok. ¿Hay más preguntas? ¿Comentarios? Ok, gracias. Ok, bueno, entonces muchísimas gracias por su atención. Si tienen preguntas, sin problema me escriben un correo electrónico. Ya mi página web está, ya van a encontrar en las páginas de SimStaff. Entonces, si hay una pregunta después, sin problemas de la optimización, cómo entrar en el SimStaff, o en el Research Experience Day, o el NEO, Numerical and Evolutionary Optimization, el taller, me escriben, no es urgente, saben cómo contactarme. Y si no, bueno, muchísimas gracias y vamos a terminar esta sesión. Gracias, nos vemos. Bueno, yo no veo a nadie. Bye.
Gracias, bye.
Adiós.